All right. Hello, everyone, and welcome. Thank you so much for joining us today. My name is John Black. I'm a customer success manager here at Citrine, and we're very pleased to have a mix of attendees on today's webinar. Some of you are already Citrine customers and know the platform well because you've been working with us for a long time, while others may be a little bit newer to the platform and just starting to learn what it can do. Wherever you are in that journey, we're glad you're here today. Before we get started, just a quick note on the format. We will leave plenty of time for a Q&A at the end, but please feel free to type your questions into the Q&A box at any point during the webinar. You don't need to wait until the end. Just add them as they come to you. We'll go ahead and get back to as many as we can towards the end of the session today. And if there are any that we don't have time to address, we'll go ahead and follow up with you on those later. So with that, I'm delighted to introduce today's speaker, James Peerless. James is our senior product manager here at Citrine, and many of you may already know him from customer interviews and product discovery conversations he's led with some of you to better understand what materials and product development teams need from the platform. James comes to us with 10 years of experience working in AI and material science. He's been with us for 7 years of that 10. And before joining Citrine, he was a process engineer in a materials company himself, which gives him a valuable combination of product leadership, hands-on technical experience, and a practical understanding of how materials teams can apply AI to real-world R&D and product development challenges. So with that, I'll go ahead and hand it over to James.
Awesome. Thank you, John. So welcome, everybody. Really excited to be here and talk to you all about one of my favorite topics, which, of course, is the Citrine Platform. But not just that. As John mentioned, I spend a lot of my time talking to users, just as much time talking to users and our customers as I do talking to our developers and trying to actually build the right things for our platform and for our users. And some of the things that I am constantly excited about is seeing the way that people are using the platform in new and different ways. We've built in sort of a core workflow into the Citrine platform, sequential learning, which I'm sure you all are familiar with. If you've used the platform in the past, and if not, don't worry, I'll walk you through it really quickly. But what's really exciting is some of the other things that you can use the platform for that also deliver value to your product development experience, your ability to react to changes in the market, your ability to share and collaborate on projects, all of these different sort of side quests that you can use the platform for on your journey to make better products. So some of the things I want to talk about today, I'm going to go through a couple practical workflows that you can use Citrine for outside of our standard sequential learning workflow. And I'm going to go through these live on the platform. So these will be live platform demos using our showcase deployment. So all of these things, presumably you can do if you're a current customer with the Citrine platform today. And if you are interested in becoming a Citrine platform customer, then you should be able to do them immediately once you sign the contract. So first one I'll be talking about is how to manage and identify sort of critical ingredients and make sure you have continuity of those supplies, how to enable your team to jump into new projects with a broader shared understanding, the ability to scale up after you leave the R&D sphere. How do we get to the next stage? How to make decisions around substitutions of ingredients, whether that is to respond to changes or to get ahead of potential changes that might be coming down the line. And also our ability to work within complex formulation spaces. And I'll be going through all of these. But before I do that, just because I know we have a mix of folks who may have some experience with the Citrine platform and folks who are completely new to it, I want to walk through sort of the standard workflow, because through each demonstration, I'm going to start from a project or from a set of data, and I'm not going to go through each little step of what everything needs on the screen, but just to orient everybody. As you look at a project on the Citrine platform, the most common thing you'll see are these 4 boxes that represent data, AI models, search space, and candidates. And that belies the core workflow of the Citrine platform, which is to have test data, build an AI model that can predict the important properties in that test data. You can then, in your search space, set constraints on the experiment that you are hoping to run, whether that be equipment constraints or just different things you want to try, exclude this ingredient, make sure you use that ingredient. And then finally, you set uh, a definition of what a good experiment would be, meaning based on the predicted properties, what would make a good material coming out of this experiment. Those are basically your performance targets. And then the platform will suggest the next experimental candidate for you to take to the lab. And the important thing about that is it's not just a list of suggestions on their own. We provide what the predictions are of the important properties. And also there's uncertainty in all of that as well, which is allows you to sort of um, decide what you want to bring to the lab based on the amount of risk you're willing to take on. So if there is a possibility of hitting a very high, never before seen performance target, but there is a lot of uncertainty in that prediction, it enables you to understand, okay, how quickly do I need an answer to this request? How much of a risk am I willing to take on? Okay, there's only a fraction of a percentage of a chance that I hit this, but I'm still willing to put the time and effort into running that experiment versus something that might be a little bit less less out there in terms of the actual performance, but is a much more certain prediction so that you're willing to run that experiment to get sort of the obvious answer. So the uncertainty is key to making sort of this entire loop work, because after this, we suggest experiments from the Citrine platform. You then go run those experiments. Whether or not they're successful, that is more data for the machine learning model to learn from. So eventually you get this sort of flywheel of being able to improve the model, even if the predictions weren't as, the results weren't as high as the predicted values might suggest. So all of that is the core workflow of building a model, setting constraints on your experiment, deciding what the best performance is, taking those suggested experiments to the lab, and then hopefully either hitting your targets or maybe you're only another cycle or two away. Either way, the candidates that we suggest should be give you the most information, if not the best performance of the experiments you could potentially run. But as the topics might suggest, it's not the only thing you can do with the Citrine platform. So I want to walk through some demonstrations. The first one being a very common scenario where you may have a important ingredient in your formulation or your final product that you're looking to optimize that may not be obvious, but you would want to get ahead of in terms of either ordering buffer stocks, making sure that you have multiple suppliers, or any of the other mitigations you might have to potential supply chain risks. So I'm going to go to a very specific project to sort of walk through this. So this project involves, this is on the Citrine platform now. This project involves optimizing lubricants for a very specific outcome, both to hit a certain amount of viscosity, but also to allow an amount of oxidation stability. And of course, you want your lubricant to reduce wear in whatever parts it's being used to lubricate. So this is a project that someone else has already created a model for me. They've already done some explorations with different search spaces, and it looks like they've generated some candidates as well. And one of the things that we can identify just by looking at the model itself is to find what ingredients are most impactful in terms of driving performance. So one of the ways we can see this is actually looking at the model evaluation. So this is just a pretty simple model that was created from our training data, which is just a bunch of previous experiments run on these lubricants. And the model evaluation gives you some information on how well the models are performing, which of course is important, but it also gives you information on what affects the performance, not just of the models, but actually of the material itself. And if we look at something like coefficient of friction, those of you who might be familiar with lubricant formulation might not be surprised to see this ingredient ZDDP show up at the top of what we call feature importances. Now, these feature importances just tell us basically the amount of this ingredient is very impactful for this output. This output being what I'm looking at now, the coefficient of friction. Now, ZDTP, if you're familiar, it's zinc dialkyl dithiophosphate. It's a very common sort of, wear reducer protection. So it might not be surprising to you to see this on top of a very important feature, as well as anti-wear additives for something like coefficient of friction. That's something that we might expect. But we can also look at other things like, for example, if we look at the RPVOT, this is around oxygen stability. We also see ZDDP show up at the top of this feature importance list too. And quite frankly, by a lot compared to the next important feature in this list. Now, this might originally or immediately raise some flags to say, okay, well, we have to make sure we have a lot of that in stock. It's a very important ingredient, both for the anti-wear capabilities, but also for our ability to keep oxidation stability high, as well as potentially some other things as well. So that's all your ability to be proactive there. However, sometimes uncertain things happen. So how can you potentially be reactive to changes? Now, this other branch that I have up top here is showing what happens if you have a sudden spike in the cost of this very important ingredient. So now, normally you could update all of these things in place. I broke out another branch just for the sake of showing you all. Ideally, you would sort of update all of your data. That gets pulled in automatically, and you can update your branch to include the most up-to-date data. In this case, I broke out a new branch just to show. In this case, we now have lubricants that have tripled in cost. Our ZDDP, for whatever reason, is much more expensive. Now, we can run with the exact same model that's been retrained. We can run with even similar search spaces so that the bounds of our experiment are the same. But we can suggest different candidates based on our cost sensitivity. Because in all of these evaluations, the previous ones as well, one important constraint has been the average cost of all of the ingredients. So what this is saying is that this is a cost-sensitive project. We need to make sure we are under a certain amount of cost. And now, if we look at some of our candidates, we can see that our costs, especially when it comes to ZDDP, we are now suggesting candidates where, to keep the cost down, the bulk of our candidates are mostly in this region here, which is a low-cost, low ZDDP formulation. And that signals directly from a spike in cost leads to a change in how attractive those candidates are to the model, and thus changes what candidates are suggested, because the sensitivity to cost is built right there within the candidate selection algorithm. So essentially, what this score is doing is penalizing a high amount of ZDDP in the formulation, especially if it goes above that 1.5% or so. So, Citrine Platform allows you to take real-world constraints, such as your cost and the cost of your actual ingredients, and puts them right into the pipeline in terms of how do we suggest the best candidates based on what the optimization targets are for your project. Now, the next thing we want to talk about is really just a common workflow in a lot of different scientific endeavors, which is you have a new member on your team and they need to get up to speed fast. There can often be a lot of domain knowledge built up around a specific project, and not all of that is tracked in the best way. What we've discovered is that the way that the Citrine platform has been designed, it has been designed to both capture domain knowledge in order to be leveraged by a machine learning model, but also in order to be leveraged by humans. Because frankly, the entire approach of our model building and our search space building, and even the way that we structure our data, uh, is around the fact that machine learning algorithms and humans work best if they enable each other rather than one sort of working on its own. And that is specifically important in the domain of material science and chemistry because generally we don't have enough data on your specific process in order to just learn everything from data alone. So as a result, we have a partnership between scientists and the model, which while making better models and making better predictions, which is great, it also has this ability to encode a lot of that domain knowledge in assets such as models and the data structuring itself that allows you to sort of pass that to the next person that you're working with. So to give an example of that, I want to start with a different project. This one is completely around optimizing a set of ABS plastics. So the entire project, I'm not going to get into all the details, but essentially you have all of these ABS type plastics, and you're trying to maximize their all of their physical properties, while also maintaining cost viability and other performance properties. So if you're just starting this project, there's a lot that's left to the user to sort of understand what is going on here. There's already a lot of data here, and that often is a great place to start just to get oriented. So if we're looking at our training set, okay, we have some very sort of basic sort of data visualizations that let you see things like, okay, this is flexural modulus. This is how flexural modulus changes with molding temperature. This gives me some idea. I often find distribution plots are a great way to get oriented with the data set. You can see we automatically highlight things that have outliers in case those need correcting, but you can look at any of the performance properties. So you can get an idea of, okay, this is sort of, these are the different injection molding temperatures we've tried. Looks like we've only tried 30, 50, and 80. Okay, that's something to keep in mind. You can also look at the spread of properties. These are kind of the impact strengths that we're dealing with in foot-pounds per inches. That's interesting. That's all great if you're just thinking of this as a data set, but of course, this is a chemical process. There's more information there. And part of our machine learning algorithms, but also just our philosophy when it comes to data, is to encode as much as the chemical process as we can. And that's where you can really click into specific materials and see the full history of that candidate, or sorry, excuse that full history of that final product, that material. So here we get a much clearer view of what actually went into that final product. Besides just a table or a scatter plot, we can see specifically what went into this material. As we see, there are previous steps, such as twin screw extrusion. It looks like in the injection molding process, we also add a lubricant that is bought off the shelf at a very low percentage. What happens before that? We have this powder pre-drying step. That's where we mix the bulk of our ingredients. So all of this really allows you to get oriented to what this process is. Now, a step beyond that is, okay, we have an idea of generally the shape of the data, what it looks like to create one of these things. But that's also carried through to the model as well. As we look at how this expert, as they called themselves, created this AI model. Now, I can quickly sort of go in and change things around and get predictions. But what's really important is the ability to look at the model and see what changes were made that might be clues into how this is created, right? So right off the bat, we see that the model is predicting out of these purple nodes some very important parameters, or sorry, very important performance properties. But when it comes to what is being used in these performance properties, we can see that whoever did this also included a custom formula. Now, this is something that is completely done by a user for a couple of different reasons. It may improve the model. It might also just be something that the user likes to track because it's a way that they think about their materials. In this case, this antioxidant mitigation factor was really important. It seems to be a function of mold temperature, the drying temperature, antioxidant, the amount of stabilizer, and twin screw extrusion. But whoever put that in must have thought it was important. So that might be useful to you as you're talking about candidates, you're talking about experiments. The values for the antioxidant mitigation factor is now computed with any candidate that you might produce from the Citrine platform. And that allows for sort of a shared understanding between two scientists, depending on who put this in. And then, of course, once we get all the way through to actual ingredients, actual candidate experiments, we now have all of this context to look back on when it comes to these are the important properties. We have all of the full process steps for a candidate that has just is about to go to the lab. We have, rather than just a spreadsheet, we have the actual list of steps. So we have a full recipe to show. And of course, some of those information that's stored in those custom calculations. Okay. Moving on to the next one. Now, scale up. As someone who has chemical engineering in the background, I understand that scale up is one of those things that you can spend your entire career, and many people do, on. It takes a lot of understanding of both the lab scale, pilot scale, and bench scale to understand what it takes to go from a successful experiment at the R&D level to something that can be manufactured at scale. One of the projects that I wanted to highlight specifically with this is a project around lithium ion cathode formulations. So when it comes to scale up, we may not have the background of data on the specific thing that we're trying to scale up. So we have to take the hints from what we've learned at the bench scale in order to do that scale up safely. So when it comes to the candidates that we suggest, we often can allow the person who is actually going to make bets on those candidates, who's going to take that information and actually say, yes, I want to run these candidates in the lab. I'm going to put the cost associated with that and the time associated with that and make it real. We want to give that person tools to make that decision on a number of different factors. So this comes back to why we have human in the loop, meaning we allow our users to select candidates as being so important. Because not just do we want the user to select the best candidates as suggested by our candidate generation algorithm, we also want them to allow folks like yourselves who are experts in their domain to make these trade-offs, such as when it comes to scale up. So even though we have scores, which basically say, based on the objectives and constraints you give us, these are the rote scores of what candidates we expect to be able to do well based on those objectives. Although often there might be multiple things that you want to consider. One of those being, how easy is this thing to scale up? And that's where having a lot of candidates that you can potentially sort through, but also the ability to filter becomes really important. So for example, in this case, if I just want to rotely take the 5 sort of best candidates according to the model, I can. That's completely valid. Those will give me a lot of information. They're expected to hit the constraints, and that's fine. But if I want to explore something else, like, okay, I'll take the top 4, and then maybe I'll throw out something else. I didn't explicitly say that I want coding to speed to be a factor. But I know as I'm scaling up, I need something that's going to have a fast coding speed, or else the manufacturing landscape just won't be able to handle it because it takes too long to produce this specific cathode type. So if I want to, I can look at, okay, I want the coding speed to be at least 5 meters per minute, right? Okay, I still have a lot of very high performing candidates. In this case, yes, we are just trying to optimize mostly up and to the right, although there are some other effects as well, which you can see, in a table view or something. Um, but then if you want to change and say, actually, you know what, I want to be a little bit harder here. So I'm actually going to say I need the speed to be at least 12. Um, and forget my high nickel ones. You can see that a lot of my up and to the right aren't there. So maybe to at least test something that has a little bit more high manufacturability, I might go with something that has a lesser score, because you can see on this plot, there is some uncertainty here. Within the bounds of our uncertainty, I might be actually up in this region. So maybe it's worth a shot in order to address some of those scale up concerns. And of course, coding speed is not the only thing. You can do this with any of the potential processing conditions or performance outputs that might be there if you want to make some new filter, right? So, okay, moving along here. As is usual with demos, I end up taking a little bit longer than I always planned. And I want to leave time for questions. So I am going to move right along to the next one.
That's okay. And James, just as a quick interruption, I'm going to go ahead and just provide a quick reminder that while James does continue, please feel free to type any questions into the Q&A box as they come up. We will have time at the end for Q&A, and adding them now does help us make sure that we triage everything. Thank you.
Right. Thank you, John. Yes, please add in questions as they come up. Okay, so I'm going to go back to our ABS project really quickly to talk about the next thing. Substituting an ingredient is often something that could be responsive, could be a way to reduce cost, could be a way to improve performance, could just be curiosity, right? You have a new ingredient, you want to get an idea of whether or not this improves or doesn't improve the performance, the cost, what have you. Part of the Citrine platform is the ability, one of our most recent features is with our data harmonizer Omni, the ability to take a PDF and ingest it very quickly. So I want to show what that could look like specifically when it comes to ingredient replacement. I'm going to go back to the ABS project really quickly. And this is very similar. Again, we're trying to optimize our ABS plastics. If we actually look at the original data set, here are our sort of our, oops, hold on. This is our data set. We have quite a few raw materials that we're mixing together here. But let's say I have a new one that just got in-house, or I'm considering purchasing one, and I'm able to get the sort of technical data sheet that goes along with this ingredient. I want to quickly upload it and then get an idea of, okay, could this work for us? To add information to our data set, we can do it a couple of different ways. By clicking on this bulk upload formulations, this is using sort of an Excel spreadsheet to upload a lot of data at once. That's a very common way to get historical data in. You can also add raw materials one by one, two different ways, manually versus a form, or we can use Omni to automatically read a PDF for us. That's what I'm going to do here. So I'm going to look for my tagged ABS data set. This is my favorite one. It has my favorite tags. I'm going to upload a new material. And then I'm going to click review. And this is where Omni is sort of doing its work. What we're doing is we're actually just looking at the data set as it exists today, trying to find all of those material properties that already exist in the data set and mapping those to what might be into this TDS. That way we don't have a bunch of new properties sort of hanging around. Like, if someone types temperature and someone else types temp, Omni is smart enough to match those two up together so that when you actually pull them into a data set, you make sure that temperature and temp are treated as the same thing. They're using the same definition of what that property may be. So this mapping happens, and then we'll put it in front of the user to make sure that everything looks right. I'm going to go through this relatively fast. We have different demos of this feature alone, but what I really want to get to is how you might be able to test this feature more accurately. So I'm going to call this something a little bit more easily accessible, just so it shows up easily. I don't really love the underscores. I'm going to call it HV80. HV80. A, and no hyphen. Okay. I'm going to look through this. Okay, it looks like we have all these check marks means that this property already exists in the data set and will get mapped. We have some new ones here. Oops. Want to make sure we go to PSI, but that's actually megapascal. Okay, so we can handle those different unit conversions there. And I'm also going to ignore some of the suggested things that come out of a mold. Let's see. Yeah. That looks good. And the biggest thing is I want to make sure we have the correct label. That looks good to me. I'm going to say ingest, and this will actually create the material in our data set. So if I'm just looking at raws, I can look at when it was last created. Oh, excuse me. And there's HV80A. Now, let's go back to our project. So the first thing I want to do is update my training set to make sure I pulled in the data. Now, and the reason this is manual, I see I have one new terminal sample. The reason this is manual is because we don't want people modeling and stuff, and then the data is changing under their feet. So there is sort of this manual refresh step. But only takes a couple seconds for the new data to be reflected in the training set. And when that is, if we go back to our project, you'll see that there's a new update. My table rebuild completed. Oh, brought me back to my table. And we should see that I can now update this branch because there's now new data available. And that's correct. So now I want to retrain my model with all of that new data because maybe there's some other stuff in there since the last update. But immediately, if I create a new search space, I can see, if I want to play around with my ABS resins, I can see really quickly that I can run an experiment where I say, yes, make sure you add this resin. And if I give this a name, I can actually save it. So now what I'm saying is I can run this experiment where I say, when you suggest me candidates, make sure you include this untested ingredient. And maybe I want to try some others that are untested as well. I just need to make sure I give it a minimum amount so that it works. Oh, and of course I'm saying you can only use one resin, which is wrong. So I got to correct that. And there we go. Now, I'll show you this a little bit later because it will take a little bit for that to train. But you can even do that in the Model Explorer as well. But that will have to be ready in around 2 to 3 minutes. So while that's training, we can move on to our last one. Now, this is really calling out for any of the workflows that we just showed. Fundamental to the way that we handle data and modeling at Citrine is built around this idea that materials are often not a linear process, that it often involves mixing things together. And you can even make measurements on those intermediate materials, and those will affect the final performance of your product. So throughout sort of all of our projects, and this is a new one, this project is focused on our creating multi-layer packaging that's biodegradable. Throughout every step, whether we're talking about the data itself, I already showed sort of the material history, the search space itself, if we want to make a new one and edit it, every part of this process involves being able to make changes that affect your final product based on the mixture the mixture of mixtures that are in its history. So if I want to specifically constrain PEF film extrusion, I can do that. I know that, hey, let's only look at the extrusion temperature of 220, and that's just for that process step. Then I can also edit the final process step as well. Maybe I only want to inspect the two extremes here of 160, 200, and maybe try something in the middle of 180, right? All of this control comes down to explicitly intermediate process steps, because we expect a lot of these problems are not as simple as a linear formulation or just mixing a bunch of things together in a pot. Each process step has its own level of conditions and its own constraints on what materials I want to include or exclude. And finally, when we get to the end of the process, or at least the goal of the process, which is to get candidate experiments, we don't just show you these experiments as flat candidates. We show you the full process history so that it's something that is actually ready to take into the lab with precise process conditions for each process step, and then precise percentages of ingredients for each process step separated out so it's easy to take to the lab and actually make the material that you're hoping to reach your goals. So with that, I just wanted to show real quick, if you do have a trained model, you can go to your explore stage and now quickly choose any molded part and see what it looks like to swap with my new resin that I just updated, which I believe was HV80A. Quickly run a prediction. We see our results. So model seems to think that tensile strength and flex mod might have a reasonable way of increase in performance if I use this new resin. So always good to leave a demo on positive results. With that, I have to show you this this slide of our partners, as well as some of our statistics, really just to show you we've been at this a while. We've helped a lot of very smart people do really amazing things. It's been my pleasure to help those people. And hopefully, if you haven't worked with us yet, you will in the future, so we can help you as well. And with that, I would like to thank all of you for your attention, and I'll turn it back over to John for questions.
James, thank you so much. That was a great overview. We're going to go ahead and move into Q&A now. And as a reminder, please keep adding your questions into the chat box, and we'll go through as many as we can before the end of the call. To get us started, James, I think I'll ask the first one. So with your 10 years of experience working with AI and material science, what would you say has changed in how companies use AI?
Yeah, I mean, it's night and day for sure. I've been with Citrine for 7 years now. When I first joined, I was actually on the customer team directly working with our customers full time. Then I moved over to, I like to say, I moved over to the dark side of product development. But originally in those conversations, we had to spend a lot of time explaining just that machine learning and artificial intelligence are things that are useful to material scientists, right? Just explain that, hey, there's this thing called AI and machine learning that our algorithms have shown that like we can really increase the time it takes to get a material from concept to market. We have experiment, we have data that shows us, we have benchmarking data, we have all this stuff, and a lot of people just weren't convinced that this was a way to develop materials. Um, Especially in the last 3 or 4 years with all of the new AI enabled products on the market, and sort of this top down in some places even a direct edict to use more AI. It's become much less about, okay, you should be using AI, and how do we use AI in a way that's successful, right? Specifically in the domain of making better material products, because ChatGPT or some of these more general solutions um, may be able to work very well with text. That's what their algorithms are based on, and they can be useful for some workflows. But if you really want predictive power, um, understanding that a AI algorithm is only as good as the data that you give it, and that most of the data that defines how your products will perform in the market are kept within your company for good reason, because that data is extremely valuable. You have to understand why these general solutions, which are just trained on generally available data, um, might not actually get you to the goal that you're at. So a lot of it just comes down to, what does AI mean to the general purpose, to the general person that we're talking to? And different people have different, very strong opinions, weak opinions towards that. Um, but that's definitely been the biggest change, is like, we've always been focused on generating new, better products for our customers. That's always been the goal. AI has always just been the tool to do it, and we continue to use the best and the best tools that we can to get there. But the conversation has shifted from whether you should be using AI to how should you use AI, and how do we not just create a whole bunch of like new pilots that don't go anywhere.
Thanks, James. That makes a lot of sense. So we have a couple of questions from the floor. So the first one is from an anonymous attendee. So James, you sort of touched on this a little bit, but they're asking which data file formats can be used and which ones cannot.
That's a great question. So our UI based ingest, which you saw one example of with our PDFs, the most common way to get data in the platform, especially if you're starting up a new project and you have a lot of data, is an Excel file, an Excel template. Um, those are the two easiest ways to get data in the platform. However, we do have other tooling supported by our Python software development kit, Citrine Python. It's open source. You can look at it. That allows you to basically ingest data from any format, as long as it's machine readable, right? So the two easiest ways are Excel and PDFs. We've just identified those as the most common. We have a lot of customers that have automated pipelines that are running on a cadence that directly take from either other sort of data lakes or other data sources, nightly or weekly, as the case may be, automatically ingest to the Citrine platform. That's one way to do it. And then any sort of one-offs, if it's going to be something that's sort of repeatable, you can use our Python SDK if it's sort of a strange format like a JSON, or you want to plug into some other external system.
That's great. Thank you, James. We have another question from the floor is, can qualitative performance data be used?
Absolutely. One of the things that's core to our modeling strategy and just throughout is our ability to handle what we call categorical data, which essentially, could be a pass fail, a binary, or it could be, um, good, bad, and different. All you have to do is just give like whatever the qualitative data is, it should have some bounds on it, um, such that it maps to a certain definite number of categories, and we can predict what those categories are, right? So that is sort of the flavor of qualitative data that we support. We've piloted some tools that sort of one-off take maybe some messy data and map those into categories for machine learning, which does work pretty well in a lot of cases. Sort of like a sentiment analysis type thing. But there's a lot of potential work that we can do there. The big thing is that categories are handled natively, which means you can use them as targets, you can use them as inputs, you can use them as uh, raw material properties, etc. Yeah.
Thanks, James. That makes a lot of sense. And here's another one from the floor. Does Citrine have a tool to help labs to standardize data format before injecting into Citrine?
Oh, I feel like you're setting me up for a what's coming next slide. So you've seen sort of Omni exposed in the previous demo of our PDF ingester, right? The the big task there and why it has the Omni label is because it's the first of many Omni features we hope to ship in the coming quarters. Um, the underlying engine is really that ability to take something that is semi-structured like a PDF and look at an existing data set and be like, okay, what are the stuff that I should map together so it's nice and defined, right? And then it puts in front of the user, here are the things that we tried to map to. Does this look right to you, right? That's obviously something that we hope to expand to other formats, such as if you hook Omni up to a data lake, if you hook Omni up to an Excel spreadsheet. Those are the things around giving guidance on how to map and how to input data in the way that's most efficient onto other file formats directly in the UI. So Excel spreadsheets, and then potentially linking up to other data lakes. So those features are coming. One of the things, just to be clear with everyone about okay, well that seems like it should be pretty simple. We take security extremely seriously at Citrine, and we often say hallucination is not an option, right? So anytime we're using some of these mapping tools and suggesting things, we want to make 100% sure that any sort of non-deterministic like LLM type tool is only mapping data and not creating or editing data. And so we're making sure that we have very, very precise walls around the data that touches Omni, because we cannot have Omni hallucinate your data, and we can not have Omni share your data with any third party.
Thank you, James. That makes a lot of sense. Let's have some more questions coming from the floor. This is great. Keep them coming. Thank you. Is there any function for generating candidates without existing data? For example, the first candidates, which can cover the best design space. I'm not sure if that makes sense the way it's worded.
Sorry, could you just repeat it one more time?
Sure. So the question is there any function for generating candidates without any data existing or minimal data existing?
We've tried that on in a couple areas. There are a couple of ways to do it right now through SDK features. We're experimenting with what is the best one to bring to the UI. Essentially, the problem is one of those where the devil's in the details, because we could ask a user to define a search space and just randomly sample that search space. That's something that we can do. And I shouldn't say randomly sample. It's like random plus. We make sure to explore the search space such that you get a certain number of candidates to start with. One of the issues there is you could imagine if you saw some of those search spaces, especially if you have a lot of process conditions, it becomes very tedious to define all of those manually, right? You could imagine that it's a lot of just like typing in your screen. So we are experimenting with tools to sort of make that quickly, because right now our search spaces are created based on the data you give us. You give us a bunch of training data that's shaped like X, we create a search space that's shaped like X, right? So in order to not put too much burden on the user defining that whole search space, we're looking at ways to make that much easier before we do that random sampling.
That makes sense. Thank you, James. It looks like we have another one from the floor. Can images from analytical instruments be ingested directly as data?
So yes, but we have our underlying data model, which you saw sort of the material history. You can attach images and really files of any type to that data, right? So that historical file data is forever associated with that material. In terms of being able to leverage that as in the model, we've done previous experiments with that. And we have some out of the box Python tooling that can be used to sort of extract that data into ways that can go directly into our machine learning models. Historically, one of the reasons we haven't necessarily built all of the UI formulation around it is just typically the amount of images we have access to isn't to the level of actually making a big difference in the predictive models. Typically, maybe we have a couple hundred images, which sounds like a lot, but to a machine learning model on image data is not. So we have some SDK tooling, our Python SDK, to enable that. We don't have UI tooling yet to make it really user friendly, just because we haven't seen the benefit to every problem really showing up as much. Primarily, what we want to enable first is just the ability to track the raw data and its association with the material before we're able to actually automatically featurize and use those really like dense data-rich image files.
Thank you so much, James. All right, I think we are coming up on time, so we're going to go ahead and wrap there. There have been a lot of great questions today. We thank you for those. We're going to go ahead and answer all of the remaining questions that we have individually as we are able. Thank you again to everyone for joining us and for the thoughtful questions. And James, thank you so much for leading the session and sharing your perspective on these things. We do really appreciate everyone's time. We hope that you do have a great rest of your day. We'll speak soon.
Thank you all.
Thanks, James.